Okay, I think we're going. Let me just get my microphone a little bit closer here. I think we're Yep, I got signal here. Good. All right. Well, welcome everybody for another Future in Space hangout. My name is Tony Darnell. For those of you who don't know, most of you guys know who I am by now. And today we're going to be talking about the future of astronomy. Because a couple of weeks ago, about 3 weeks ago, I guess now, the astronomers in the United States got together in their little covens that they gather in, and they met and they talked and they discussed all of the different things that they wanted to learn, and they decided important issues like dress codes for conferences. No, I'm kidding, they didn't do that, but they did sit and talk about what they wanted to know. The great thing about science is that it will, it knows what it wants and it knows what it needs to know, and they don't want to proceed until they can get a good idea of what and how to go about learning the things they need to learn. And astronomy is one of the, I don't know about other fields, but I'm most familiar with astronomy. And I guess physics may do the same thing. I'm not sure. But they get together every so often to decide how they're doing. And what are the big questions in the universe right now that they'd like to have answered? And so they meet and they discuss these things. They prepare all these reports, and they're actually very influential reports because they guide the direction in which science and in particular astronomy research is going in the United States. I don't know about other places, but at least that's what the United States does. Other countries may do something similar. I just don't know. So we're going to talk about some of that stuff today. I got to be honest with you, though, I was woefully unprepared for the amount of work that this hangout would entail. For those of you who don't know what I usually do twice a week, sorry about Tuesday. I just got too busy. I couldn't stream on Tuesday, but on most Tuesdays and Thursdays, I put together a talk and we go over it together about a particular topic and we discuss it over a live stream. I like live streams over videos because they're much more interactive and they're way more interesting to me. It's really, I mean, I've been at this since 2006, and recording a video, editing a video, uploading the video is nowhere near as satisfying as streaming. And now that I have this ability to go live, I like to share things with you guys directly. So that's my preferred form of content making these days. It isn't necessarily reflected in my viewership numbers, but I'm fine with that because I really would rather have a small group of people who want to talk about these things and share and kind of get together, than having millions of people that I don't know watch something. So I mean, that used to be gratifying, but now I much more prefer this. So how are you guys doing? And you're probably thinking, well, how can I tell you how I'm doing? So I'm streaming on Twitter, Twitch, uh, Facebook, YouTube, and I have this thing where I can conglomerate all the chats into one thing. So I can look at all the chats and I can see who's out there. For example, here's Kenneth, and he's saying hello. Hello, Kenneth, on YouTube. And Nirud is commenting 1 month till JWST. Yes, we gotta think about what we're gonna do for JWST. Gotta do something, don't we? So I'm still thinking about. Oh, by the way, look in the description. If you're on YouTube, see if you can see my JWST t-shirt that I just made. It's expensive. It costs $25, but that's the minimum. That's what Teespring charges for that. I don't make I didn't mark it up at all. But if you see it there, it should be underneath this video where all the other little gear that I have is. And it's cool. Let me just tell you about this t-shirt. If you don't see it now, you hopefully see it in upcoming videos and streams. It uses the JWST logo from NASA, which is the official one now, which I kind of like. I thought was a pretty good one. And then, but the shirt itself is one of those all over prints. And those stars are the data from the highest resolution image ever taken by Hubble. It's the panchromatic something I forgot now, survey of M31. It's they call the PHAT survey of M31 in the Andromeda Galaxy. Those are the highest. That's the highest resolution image Hubble has ever taken, and it's only of a portion of M31. So that is the base of that shirt. And then on top of it, I've got the logo on the front, and in the back, it's kind of a cheesy little nerd thing where I just show the differences, that the graphic that you've seen many times, of the size of the JWST objective and the size of the Hubble objective, with a little person standing there for scale. So I don't know. I made that. I don't make any money on it, but I wanted to make it for us. I've ordered one, and you're saying it's not coming up. So let me see if I can do something. I just want to. It's one of those Teespring things, and I chose it because I could attach it to my my YouTube account. So let me just log in real quick. I am not a robot. Okay, log it in. I'm going to get if you go to my store, which is like spring.com, deep astronomy or some nonsense, you should be able to see it. Yeah, it's right there. So let me share the link. Copied, and I will now share it here. There it is. I posted it in the chats, so you should see it in there. And it's $25, but that's not my fault. I guess it's expensive to print these things. Anyway, I thought it'd be kind of cool for us to have one of those, so I made that. Enrique, how you doing, man? It's good. Ebone, that's Ebone. It's good to see you. I'm glad you're here. And I was just talking about a t-shirt that I just created for JWST, a little thing. No proceeds go to me, so don't worry about it. Yeah. So, oh no. So Hans, it won't be in there. It won't be in the description box. It'll be underneath the video part itself on the YouTube page of this video. You know how sometimes when you go on video on YouTube, you can see the merchandise for that creator. It would be there. I just put it there, so it may take a while for it to do. And I will put it on Discord. Let me just do it real quick on Discord too. While I've got the link in my clipboard. There, it's on Discord too. So there you go. Okay. All right. Get through a couple more. So I'm gonna get going because I've got a lot to talk about. So let me hide these. Okay, so the format is I'm going to go through my slides real quick and not look at the chat, because if I look at the chat, I'll get distracted and then I'll lose my train of thought and I won't be able to go forward on this. So I will get back and we'll talk about this. You can also join the Discord server if you like and go into the live stream voice channel. Your audio will be piped into my earphones and I will be able to hear you, and then I can patch you into the stream. So it's kind of like a call-in show, but not really, because no one ever does it. A few people do, a couple people, but there's nobody there right now. Just be aware that when you go there, you're probably your mic. Try to mute your mic, because I've got that live right now. It's going to go straight to the stream because I'm going to show a video on this in just a minute. All right. Let me share my screen. Oh yeah, there's the t-shirt. Let me get rid of that. Okay, here's what I want. Whew. Okay. Let me hide this. Okay, so like I said, boy, I really had I had quite this report was huge. I am still going through a lot of it, and I was getting bogged down into all the details, because to me this is really interesting and I wanted to read everything that they had to say. But I still I'm getting through this getting through this report, and I was making these slides and I'm basically putting everything in the in the report, in the slides. I'm like, wait a minute, this is going to be too long. I can't go through all this. So I won't be covering everything that can be covered, but I will be talking about the highlights that stood out to me, the things that I think you will find the most interesting and that I found the most interesting so far. Now, we may do another follow-up on this where we talk about other aspects that I didn't get to today. But But for now, this is it. This is so there's this Decadal Survey that comes out. It's late this year because of the pandemic. It usually comes out earlier, but it's only just now coming out. So let's start with what the big questions are. This is what they've identified as the key things that astronomers want to know, and they've put it into these three themes here: worlds and suns in context, new messengers and new physics, and cosmic ecosystems. And probably the most number one thing that astronomers want to know more about are exoplanets and Earth-like worlds. And so that's one big critical thing. It's the understanding the connections between stars and the worlds that orbit them, from nascent disks of dust to gas to the formation and evolution. Through formation and evolution is an important scientific goal. And the effort to identify habitable Earth-like worlds and other planetary systems and search for biochemical signatures of life that will play a critical role in determining whether life exists elsewhere in the universe. That's one thing they want to know. Another big thing they want to know is over the next decade, they want to use a range of complementary observations from gamma rays, from radio waves to gamma rays, gravitational waves, neutrinos, and high energy particles. And they want to use all of those different wavelengths to do investigations into the most energetic processes in the universe and address larger questions about the nature of dark matter, dark energy, and cosmological inflation. These growing capabilities will enable closer study of neutron stars, white dwarfs, black holes, black hole collisions, stellar explosions, and the birth of our universe. That's another big theme. Finally, cosmic ecosystems. They want to understand the origin and evolution of galaxies from cosmic webs of gas that feed them into the formation of new stars, and new observational capabilities across electromagnetic spectrum, along with computation and theory, will help resolve the rich workings of galaxies on all scales. Now, there is an entire chapter 2 of this report, which is dozens of pages long, that goes into a lot more detail about what those three themes are. But that's the overall thing that they want to know about. So the highest priority, the biggest takeaway from all of this, is lessons that they seem to have learned from the James Webb Space Telescope. They want to, okay, so let me just take a step back here. Usually this report outlines the things that astronomers want to know, and then it goes into a bigger detail of prioritizing what should be done, what spacecraft should be built, what telescopes should be built, what observatories should be built to answer those questions. And in the past, they would make a list of recommendations of the things that they would want built. Build the Hubble Space Telescope, for example. Build a big observatory that can characterize dark energy. That would be some things they would say and go do. And they would just go ahead and prioritize that. Well, this report is the first one I've read over the times that I've been doing this. It's different. They don't do that in this report. In fact, they don't give any specific mission recommendations in this report at all. Instead, what they do is they recognize, hang on a minute, we need to rethink how we're doing, especially large missions. And so the biggest thing they want to do is change how we're doing things, because they realize, first of all, JWST, let's use this as an example. I think this is what really got them going. It's taken 20 plus years to get built and developed. I did a whole history of the JWST in a previous video, and $10 billion to do. And so by the time they lay out the questions and priorities, by the time this thing gets launched and built and operated, too much time has passed and too much money has gone into it. Plus, there's a lot of risk involved when you say, let's build a telescope that can do all of these things, but the technology doesn't exist yet. That was a big mistake they made with JWST, they felt, was that they didn't say these words. I'm interpreting the way I'm reading this report to you. Is like that a big mistake was that, they needed to kind of test out these technologies a little bit better before they commit to building tens of billions of dollar spacecraft. So the big takeaway here was we need to change how we're doing big missions. Develop the Great Observatory's mission and technology maturation program. That's the biggest thing they want to see done. Now, Great Observatories is a program that NASA has been wildly successful. It includes Hubble, Chandra, Spitzer, and other that I can't think of right off the top of my head. These are all very large, multi-billion-dollar observatories that did everything they were supposed to do and were wildly successful. But the mission architecture was such that it took too long, and now it's getting too unwieldy to operate quite that way. It's tempting to want to keep doing that, but we need to change how we do business. So they want to see, they're calling it the Great Observatories Mission and Technology Maturation Program. I'll talk about this a little bit more detail. They want to implement a mission architecture that allows for a reasonable assessment of budget profiles, scientific performance, and technology risk. And they want to build a large suite of observatories over the next 30 years. But to do that, we're going to have to do things differently. So across the board, these things take 10 to 20 years before they even launch. And one of the things they want to see done is they would like to see implemented a probe class mission in the category of about 800 million to $1.5 billion range. And we'll talk about that in just a bit more. But this is one of their biggest recommendations. Here's an example. So the past mission, these are all great observatory past for great observatory missions. Okay, there's the Hubble, Compton, that was the one I couldn't think of, Chandra, Spitzer, and then of course we've got the JWST and the Roman Space Telescope coming up. Those are called great observatories. These are flagship missions. And what was surprising to me was this: Hubble was launched in 1990, took 18 years to develop, and actually adjusted for $2020, it costs the same, more or less, as JWST has costed. JWST is on order of $11 billion right now, and that was in Hubble was a little bit less than that. So that was very surprising to me. But these things are taking 18 years, 14 years, 17 years, 11 years for Spitzer. And all of these are costing into the billions of dollars. And of course, JWST took 21 years to develop with $11 billion cost. And the Roman Space Telescope is 14 billion years. So this is how much things have cost in the past. Here is how much the future missions were slated to cost. Now, I've done hangouts on every single one of these missions. Remember, the Decadal Survey asked for proposals for 4 different missions, LUVOIR, HABEX, Lynx, and Origins. And they did that. They submitted their reports. But the report didn't recommend any of those specifically. But here's their cost, right? The development time was on order of 2 decades for LUVOIR, 17 years for the smaller version of HABEX. These cost estimates were anywhere from $8 billion to $17 billion. So this is not, while the instruments once they're built are great, this is not a sustainable model going forward. So here's what they want to do. I don't know about showing you this, but this came out of the Decadal Survey, and this is how they want to do things now. It's a little bit complicated. I'll go through it real fast, but there's all these different missions 1 through 4. They got different color codes. But let's say in the future, somebody wants to build a big mission. Well, what they wanted to do is they want you to submit to the Decadal Survey the science case, the recommendations for all the different technology programs, and its estimated cost. They will say yes, go ahead, or they will say don't go ahead. But let's say they say go ahead and do it. Then they will want you to do a technology maturation. They want you to build the technology on a smaller scale and then implement it over a period of time. Then they'll make a decision whether or not that's a go or not. And if it's a go, they'll say, go ahead and build it and launch. So there's an iterative process here. They'll say, yes, you want to make a big mission, but wait a minute, let's do a smaller scale version of that mission, see if it's going to work, mature the technology a little bit. If it does work, then you can go ahead and launch these things. The Decadal Survey gets involved in 2 key points in this to say if you're on the right track. And then if you need additional maturation or whatever it is of the technology, then they'll go through that first. It's an iterative process that doesn't commit to a lot of risk up front. You start smaller and then you build up into bigger increments. Now, this is a really simplified version of what they want to do, but I just wanted to show you. So, using this new approach, they said, which they want everybody to start doing. This was the biggest recommendation now. We got to change how we do big missions. And so one of the first thing they want to build is a large infrared optical UV telescope that looks at exoplanets and also does general astronomy. Now, you would think that they would chose LUVOIR B for this, but they didn't. They said it's based on that technology, but again, they want to get started with building something similar to this, let the technology get mature over 6 years, and then start building it into a probe class telescope. And by doing it this way, they will balance the science they need to do with it being timely on a reasonable basis. Within 10 years, they want to get this stuff done. So while you're doing this, the additional recommendation, oops, hold on. That's not what I wanted. While they're doing this, they want to start work on a far infrared and a high resolution X-ray telescope. So nobody really won this of the 4 major programs that were being considered. Remember, I told you it was HabEx, LUVOIR, Lynx, and Origins. Those were the 4 biggies, and it was going to be kind of like a big game show where there was a winner at the end, but none of that actually happened. They didn't pick any of them. They said we want a LUVOIR-like telescope, but not LUVOIR B. Now, I thought about reminding you of what the difference was between LUVOIR A and B. LUVOIR A, I have videos for that. And the LUVOIR A was going to be a 15-meter telescope, huge, massive telescope. LUVOIR B was going to be an 8-meter class telescope. But they don't want that. They want something that is a little bit smaller and more suited to looking for exoplanets and Earth-like exoplanets. And because a telescope that can do that is also useful for general astronomy. To me, that telescope, the one that's being outlined right now, is the true successor to the Hubble Space Telescope. Everybody says JWST is, but it's kind of not. What JWST is a really big infrared telescope. This one would be the actual successor to Hubble because it's got UV capability, optical capability, and infrared capability. So that leads me to a video I did. The real winner, I think, of the Decadal Survey is the Carl Sagan Space Telescope. And instead of going through all of that again on what the Carl Sagan Space Telescope was, I'm going to use some content I already created way back in 2019. There's this weird looking guy, and hopefully I'm going to start. I've queued it up where I want to start. So let me do this, and let me do this. Brings me to the Carl Sagan Observatory, or the Carl Sagan Space Telescope. Now, I was reading a very interesting white paper written by some amazing people in the field. Heidi Hamel from Aura, John Grunsfeld, which was an astronaut who repaired Hubble for the last time, Ken Sembach, the current director of the Space Telescope Science Institute, and even Anne Dreen, the wife of Carl Sagan, and many others were listed on this white paper. And they are making the case that in order to find planets like ours, we need the capability to directly image exoplanets around other stars. Now, the telescope would be specially suited to its task. The Sagan Observatory would be a 12-meter class space telescope. That's 40 feet for us Americans. And here is what it looks like compared to Hubble and JWST. And as you can see, it's a whopper. It's way bigger than JWST. So the white paper went on to explain what else this telescope would need. It would need to provide reflected light spectroscopy of dozens of planets around nearby stars. Now, it's important that this is measuring not the light from the star, but the reflected light of the star from the planet. It's a big difference. And as you can imagine, this is a tall order. But the spectra from this light will tell us whether there is water there, in what form, whether there are any biosignatures that would signal plant life, and what the compounds in the atmosphere of the planet might be. So this is an important measurement. A 12-meter telescope would be large enough to enable direct imaging of planets in solar systems like our own. It would need some mechanism, though, to block out the light from the star because the star is really bright compared to the planet. So it would need something like a coronagraph or a star shade to get higher contrast observations. Now, using such a system, Hamel et al. Estimates that for the likely fraction of Earth-like planets in a habitable zone, let's say n sub Earth to be between 0.05 and 0.2, then the Sagan Observatory would have the capability to characterize dozens of Earth-like planets. Here's a simulated image of what the 12-meter optical component of the Sagan Observatory would see around nearby G star. If this were our solar system, the Sagan would see Venus, Earth, Mars, Jupiter, and Saturn, along with, and this is important, the spectra of the reflected light from the planets themselves. Here's an example of the resolution improvement of a 12-meter class system compared with Hubble. Now, from this image, you can see the limitations of a 2.4-meter telescope, which is what Hubble is, and why all future scopes are so darn big. Now, what matters now in providing observations that answer some of the most pressing questions in astronomy right now is resolution. So, the white paper concludes with this, quote, "We assert that Astro 2020, that's the name of the upcoming Decadal Survey, should endorse the idea of accomplishing the long-standing decadal and scientifically compelling goal of finding the signature of life on another world. We also encourage Astro 2020 to recognize that to do so requires high resolution, high sensitivity UV optical capability," end quote. And they also propose putting it out to the L2 point where everything else is going these days. It's a popular place. So as I was reading this, I kept thinking, well, just pick LUVOIR. Why make the case for a special telescope designed for this? Okay, so to review, for those who didn't watch my hangouts on this, LUVOIR is a proposed 15-meter telescope, bigger than the Sagan Observatory, and would be designed to be used with a coronagraph, a starshade, or both. So it's pretty flexible. And this would have more than enough resolution at 15 meters, and it would include a high definition imager that could image from the near UV to the near IR with enough wavelength range to make the observations required. It also has a multi-object spectrograph and a UV spectropolarimeter. So based on what I know about LUVOIR, it's a pretty good bet that it can make the observations that have been advocated by the authors of the Sagan Observatory white paper. HABEX, on the other hand, is a much smaller telescope, proposed to be between 4 and 8 meters, but reading their final proposal, it looks... Okay, I'm going to stop it there. You get the idea, right? So it turns out that the Astro 2020 Decadal Survey exactly listened to them in terms of what they would recommend. The highest priority was exactly what they had outlined there. We need to have the capability to directly image an exoplanet from around another star. And not only that, but we need to be able to detect if there's an atmosphere in it and what that atmosphere is made of. Now, JWST will have limited capabilities to do this with its near spec instrument, but it's not going to be able to have it. It's not going to be able to look at many Earth-like planets and sized planets very easily. It does have the coronagraphs that block out the sun's light, but it won't have something like a star shade or something similar to block out and get higher contrast views of the exoplanets themselves. So that was they agreed. Astronomers looked at that and they said, yes, we agree with you, Heidi. In fact, I've reached out to Heidi, or I haven't yet, but I'm going to reach out to Heidi and see if I could get her on a hangout and talk more about this. She's a really amazing person and she's super busy, so don't hold your breath, but I will try and reach out to her and see if I can get her on this hangout. We could talk more about it. But but even so, since I made that video, with the recommendation of the Decadal Survey is such that, well, even this was remember Sagan was supposed to be a 12-meter telescope, and the upper LUVOIR A was 15 meters, LUVOIR B was 8, and they didn't even go for LUVOIR B because let me see if I can bring up my slides back up again. Here is a really cool let me bring this up. Here's a really cool graph that was in the Decadal Survey present that shows this is a graph that on the bottom it shows diameter of a mirror in meters, and on the y-axis is a log scale of the expected number of Earth-sized planets that you could see with a given diameter telescope. Now, this red dot here is kind of marking the inflection point. This is, for a little bit of aperture increase, you get a lot more bang for your buck. The number of exoplanets goes way up over here. But by the time you get to about 5 or 6 meters in diameter, the returns start to diminish and the costs go even higher. So while LUVOIR was in this range, or I should say, there's different ones. This is a segmented telescope versus a monolithic telescope. So we would be probably looking at this dotted line here. LUVOIR was going to be 15, and then LUVOIR B was going to be 8. So that would put us up here. But the difference between an 8-meter scope and a 6-meter scope in terms of number of observed exoplanets isn't that much greater. So they're prescribing something on order of a 6-meter diameter telescope. That's what JWST is, but optimized for looking at exoplanets, which JWST is not. So that's why I think they didn't take LUVOIR B either. Even though LUVOIR B would have been in this range, it would have been up here. The costs, I think, would have been extremely high. Remember, the costs were, what was it? Here it is. LUVOIR B would have cost something on order of $17 billion in 2020 money. I don't. These are different ways of cost estimating. TRACE versus this one. I don't know which is which because I don't care. But there's still a lot of money. So stop it. Shouldn't have put that in there. So that's why I think they chose and basically that means that the Carl Sagan Space Telescope, with the exception of its diameter size that they had put forth in that white paper, is going to be the winner here. I think that's great news. So, okay, so let's move on. I got a lot to do here. So keep going. Keep going with stuff that's already underway. The Decadal Survey says, "Hey, keep the Grace Roman thing going. That's good. That's a great observatory. Don't stop with that." Vera Rubin, keep going with that. That's the LSST ground observatory that's going to see first light next year. TESS, keep it going. They want to see upgrades to LIGO. LIGO's already got upgrades coming up, and keep the Neutrino Observatory IceCube. But they also said, okay, you need to start, NASA, please start a probe class mission category. There's too big of a gap between Explorer class missions, which cost about $800 million, and the great observatories, which are in $5-10 billion range. They would like to see a probe class mission of on order $1.5 billion, with a cost cap of $1.5 billion. And they would like, as an example of that, they would like to see a telescope built that complements the Athena X-ray telescope that's being launched by ESA, because Athena won't have a high enough resolution to address many of the questions they have for this decadal survey. And they also would like to see an early cosmology probe that would look at the cosmic microwave background of the probe class category, and they don't have that right now. Right now, it's either Explorer class mission all the way out, or a great observatory, right, of the multi-billion-dollar variety. There's no in between class, and they want to see that because they want to implement it for that new maturation workflow that they've developed. So I'm going to rush through ground-based observatories because there's so much there too. But they would like to see the United States continue with at least one of the extremely large telescope projects that there are. Right now, there are 3. There's 30-meter telescope, the Giant Magellan Telescope, and Noir Lab, the near optical and infrared telescope. They would like to see those because their conclusion is, because of their transformative scientific potential as well as their readiness, we can do this. The success of at least one U.S. ELT is a critical priority for investment in ground-based astronomy. This is handled not under NASA's purview, but under the National Science Foundation, which handles most of the ground-based observatory work that we do. They would like to see a next generation very large telescope. This is a ground-based radio telescope that could have up to 244 antennas, and it would be able to see protoplanetary disks on scales 20 times finer than what ALMA can do. ALMA is right now the premier radio telescope in the world. It's high in the Atacama Desert, and they would like to see a next generation very large telescope built, a very large array. That should be a VLA, not VLT. VLA is currently in Socorro, New Mexico. It's that that array of radio dishes you saw in the movie Contact with Jodie Foster. That is old, and it is in need of upgrades, and so they want to build the next generation one of those. And this will also replace the capability that was lost with the Arecibo Observatory that crashed down last year. So the conclusion here is that it is of essential importance to astronomy that the JVLA and the VBLA be replaced by an observatory that can achieve roughly an order of magnitude improvement in sensitivity, and with the ability to image radio sources on scales of arc minutes to fractions of a milliarc second. That's much less than what ALMA can do, and already that's an amazing capability. Okay, gravitational waves, big emphasis on those coming up. They want to keep upgrading LIGO. There's a new upgrade coming up in 2024 called Voyager, and that begins operating in 2024. That gives everybody additional sensitivity, and they want that done. They want to keep, this is our ground-based laser interferometer gravitational wave observatory. That's LIGO. They want to keep going with that, and they also want to stay heavily involved in LISA. The LISA mission, this is what they say about this. This is huge. ESA's LISA mission remains a very high priority for the U.S. community, and NASA contributions of hardware and data analysis tools are essential for ensuring the full scientific capability of the mission is achieved, as was envisioned in the 2010 Decadal Survey. They wanted it, they call it New Worlds, New Horizons. They said they wanted it then. They didn't get it. They got canceled, and ESA took it up, and so they want NASA to stay involved because it is essential to maintain a vibrant U.S. community to keep this going. They want to, in other words, stay active in LISA. And the recommendation is that NASA should work with the European Space Agency to ensure the LISA achieves full scientific capability envisioned by that last Decadal Survey 10 years ago, and they should continue calls for the LISA preparatory science with a known cadence during the decade. After a jointly developed plan for LISA, data analysis and management are clear. And a few years prior to launch, NASA should establish funding for LISA science at a level that ensures U.S. scientists can fully participate in LISA analysis, interpretation, and theory. In other words, give them money so that you can stay and get access to that data, because it's going to be vital. LISA, I can't believe NASA dropped the ball. Well, they didn't do it on purpose, but they dropped the ball on this, and ESA took it up, thank God. So the recommendation is to stay involved in that. And here's what they say about Nancy Grace Roman. This is WFIRST. You gotta have this thing. We said we needed it back in 2010, and because it will carry out cosmological measurements complementing those of Euclid and the Rubin Observatory, and the microlensing survey will probe planetary occurrence over orbital separations not constrained by Kepler or TESS. So it's better than both of those. And the scientific landscape of these capabilities have changed. Oh, this is actually interesting. So the conclusion they came to was, you know what? This is not going to do what we initially said we wanted it to do, because remember, it got canceled. WFIRST got canceled and was only reinvigorated when the National Reconnaissance Office gave NASA two Hubble chassis, Hubble optical systems. And when they got those, this was not the original design of WFIRST. And so what it does now is not what it was initially intended or needed to have done. So so the recommendation is that they should hold a review of this science program and try and get an appropriate mix of what we actually need it to do. And they need it to do things like weak lensing, measure baryon acoustic oscillations, supernovae, and microlensing programs, because this is not what it was initially. It's not a part of the original design they had started because of the NRO chassis. Okay, SOFIA is probably the biggest loser in this whole thing. Basically SOFIA costs too much, and it costs the same amount to run as Hubble and Chandra, and yet the scientific productivity is significantly lower. There is no evidence that SOFIA could transition to a significantly more productive scientific future. So they want to close out operations by next year, or in 2 years, which is what NASA planned to do anyway. So SOFIA's getting canceled, and I think that is it. That is the last of my slides. There was like crazy amounts, so much more I could have gone into with that survey. But those are the things that stood out to me. Um, I think I know that seemed kind of boring when I was talking about the budgets and how these things get paid for, and that new approaches need to be made. But to be honest, I think that maturation program that they want to implement is they want NASA to implement it because it's NASA that has to do this. Is a good idea because think about these next 10, building LUVOIR the way we built JWST. I think is stupid. The risks are getting increasingly higher with each one of these telescopes, and so they want to say, okay, you know what? When you think of a mission like LUVOIR, think about ways that you could break the science up into smaller chunks and do it incrementally, reduce the risks. So, LUVOIR would have been this big, wide sweeping thing that would have had all these different wavelengths. Um, but they would have done a lot of different science all over the place, different kind of science use cases. Let's narrow it down a little bit. Let's build a large ultraviolet optical infrared telescope that is optimized for looking at exoplanets and Earth-like worlds. Let's do that. And a telescope that can do that can also do other things, maybe not as well as a 15-meter telescope, but it can do a lot of things. And that's exactly what Heidi Hamel and those guys were promoting when they talked about the white paper. The white paper, by the way, I put a link to that in this Hangout because the link in that video that I just showed you doesn't work anymore. So I have to change that link. I guess you got to get a password now to get that white paper. But I downloaded it and I put it on a Google Drive folder so you can look at it if you want to yourself. They were proposing a 12-meter class system, but they were doing exactly what the Decadal Survey was asking for. Let's break this down into smaller chunks and not try and build these giant sweeping things. As it is, it's going to cost $5 billion. I don't know if they're going to call it the Carl Sagan Space Telescope, but I think they should. And so that was probably the biggest winner, I think, of this Decadal Survey. So the future looks great if you're interested in wide wavelength space telescopes like the ultraviolet, because Hubble it's currently down again, and its days are extremely numbered. It's the only thing that can do ultraviolet, so we need that capability. Optical as well. JWST is only infrared. They descoped it back in the mid 2010s to only do very deep IR, and so that's where we are. Also good news for gravitational waves. I'm really happy about the LISA news. We should have been building LISA to begin with, but ESA's doing it, and we're going to have a major role in that. I think that's great. Also, the ground-based stuff, which I didn't even get to. There's the Daniel Okoye Solar Telescope, DKIST. Daniel K. I forget what DKIST stands for, but anyway, it's a new solar telescope that's being built on Maui. You've heard Jeff Kuhn come on this channel and talk about this. He's one of the principal scientists involved. That is coming online next year, and that is, they say keep going with that. Build the next generation VLT. Let's keep going with that. Let's upgrade LIGO. Let's keep going with that. Let's stay involved in LISA. Let's keep going with that. So there's a lot of good news here for the future, and I think we're about to be smarter in how we pay for it. The JWST model has got its problems. You can't, as tempting as it is to build these giant space telescopes that can do all of these things that we wanted to, they can be built and they can answer the science questions that the Decadal Survey wants answered. There's a lot of risk in this that can take usually 2 decades, 20 years to build and launch. And that's too long. So is there a faster, smarter, less riskier way to do this? And that's what this whole maturation, great observatory maturation thing is all about. Plus the addition of the probe class missions for NASA, I think, are important too. This would open up things. For example, New Horizons to Pluto was a Explorer class mission, $500 million, right? But there's a big jump to go from that to a great observatory like Hubble or Chandra, right? We're multi tens of billions of dollars. So there needs to be some interim working there. So I think all of this is good, and I think the science priorities are very good as well. I think, you know, learning about exoplanets, using this thing called what do they call it, where you can detect some, they have a phrase for it, and it's eluding me right now, but when you detect a gravitational wave event like two black holes merging, and you detect it on LIGO, you can also get then the other wavelength observations like gamma rays, X-rays, and stuff like that. So you can see these other wavelengths almost right away and match all that data together. All of that is a huge priority. To be able to do that better is, I think, where they're heading for that. Let me show you. It was a really cool. Let's see. I think it was in chapter 2. So here's I've got the report right here. I'm going to get to questions in just a minute. I just want to show you this one really cool graphic. So it's this is the science chapter. Chapter 2 is all the different science they want to do, and the section on gravitational waves. Here we go. We're getting up there to it. I thought this was a really innovative graph. I thought I had put this in my slides, but I didn't. Here it is. So here is a plot or a graph. Let me make it big. As big as I can anyway. This is the PDF. I found this very instructive. So here is a graph of gravitational wave events versus what you need to be able to see them. So up here to see right now, we've got LIGO, which is this picture in the lower right. The terrestrial interferometers can see things like pulsars, supernovae, compact binary and spiral mergers, smaller black holes. That's what we're observing right now. It's down here. But we'd like to be able to see with these space-based interferometers like LISA, we can see things like supermassive black hole binary mergers, compact binary, a wider range of these compact binaries, extreme mass in spirals. These are collisions of higher masses. So these are the kinds of things we would get with LISA that we're currently not getting, because right now we're only looking in this part of the I don't know what you call it. It's the spectrum, gravitational wave spectrum, I guess. wave period, I guess, is what that's called. So that's what LISA will get us: supermassive black hole mergers, things like that. Okay, so man, sorry that took so long. All right, let's see what we got here. So Stephen Porter on the YouTubials. Do you think we'll ever work out what dark matter is and its effects on us? You know, a year ago, 2 years ago, I would have said, yeah, we'll have this figured out. But now I'm starting to wonder if these MOND guys, these modified Newtonian gravity guys, might be onto something. I've been reading some papers. I don't know if I understand them yet, that make a pretty good case that maybe we don't need, maybe there is something on gravity on large scales we don't understand. So maybe there is no dark matter, right? I don't know. But I do think we'll work it out eventually. Sure. So let's see. This is from sorry, I'm going back. Brandon Fraser. What about a focused efforts to build VLBI telescopes out of smaller sites? Wouldn't they be more effective for less money? Design one site, then duplicate it all over the world. Well, yeah, but you get that even with, I mean, we're talking, what did they say? The next generation VLT would have been, I'm sorry, VLA would have been, where is it? 244 antennas and a slightly higher gigahertz range. You can still plug in to one of these really long, very Earth-sized interferometer telescopes. You can still get that. So, but I think this ability to do something like what ALMA does, only on finer scales, is definitely important. ALMA has its limitations. On JWST, this is from John. If one set of mirrors does not open properly, it will mean the loss of just 3 mirrors. 6, if both panels don't open, can it still operate with reduced capability under those conditions? Yes, because they are each individually movable, each segment. But we're talking a dramatically reduced resolution ability. It would be close to catastrophic if that happened, just because the resolution won't be there that's necessary to do the kinds of things JWST would do. Sorry, Amazon's here. Okay, it's all right. It's all right. It's okay. It's okay. It's all right. Sorry about that. Uncle Bill. Yeah, hi, Uncle Bill. I just heard a podcast saying the report was 600 pages. Major. Thanks, man. Yeah. Wow, it is. Yeah. So I'm still going through it. I'm still finding things that are interesting, but it was. I didn't realize the kind of advanced work I was going to need to do for this stream. But even then, I would have been at this for hours and hours. So I cut it way, way, way down. Stephen Porter. If we ever made contact with extraterrestrials, who do you think they would contact, the military or scientists, as they would be far more advanced than us? That's a good question. I don't know that they would know which one to contact. I think they would just be. It depends on what you mean by contact. If you're talking about a in-person meeting, who would they reach out to? That's one thing. If it would be a signal that we received, I don't think they have much control over who sees that. Depends on the frequency. If it's an X-band, high, high high power X-band transmission, then only NASA's going to hear it anyway, because they're the only ones with the receivers that can hear it. But if it's something on order of what SETI is doing, then I don't think they'd have much control over that. So, question: what's to be expected from Hubble from now on, and what can we expect from Vera Rubin's Telescope Observatory? Regards from Europe. Hey, thank you. It's good to have you, Miladen. I'm glad you're here. Vujovic, is that right? So yeah, thanks for showing up. And well, I mean, Hubble is down right now. It keeps going. Right now it's just on its last legs. I mean, they're going to keep it alive as long as they can, but the telescope is old. The last servicing mission was 2009. So 2019 is 10 years. So that's what, 12 years ago. This was serviced, and it's in a high energy area where a lot of cosmic rays, lots of things can happen to it up there. So it's not in great shape right now. It has well performed past what they initially thought. They always say 5 years. We're well past 10 years now on that. So we can't. For what can we expect from Hubble from now on? Not much. More images as long as they can take them. But it's still got observing programs where people are, asking for specific observations. They'll try to get through that program as best they can. But I wonder about things like the Hubble Heritage team. Hubble Heritage gets a certain amount of a telescope time to take those pictures that we see every anniversary. The ones whenever you see a Hubble calendar, or you see a beautiful picture from Hubble for its anniversary, those kind of images. I wonder if they're going to get time for those. I think that's probably going to be the first thing to go. Vera Rubin, on the other hand, that is happening next year. I think it starts getting commissioned, and we're looking at images of the entire night sky a few times a week. So this what they call time series astronomy, this thing where you can look for things happening over time, things like asteroids going by us, planets eclipsing stars, supernovae, black holes transiting between us and background stars. All of this stuff is time series. It's stuff you need more and more. It's like frames in a movie every time you take an image of it. That is where it's going to just blow up. Figuratively, not literally, astronomy. We're going to learn so much from that. We're going to discover things. We have comets we've not seen before, asteroids, near-Earth objects, potentially hazardous asteroids, black holes. I think all kinds of stuff we're going to find that we just didn't know, because we need to see time series, frames in a movie of a black hole, passing in between us and a background star and getting, microlensed, things like that. Of course, exoplanet research will also explode as well. We'll be able to see a lot more transits than we currently see now, too. So, let's see. We already know where this is from. Abdul Kader. Do we already know what those 12 Earth-like targets are? Uh, yes, they have a good idea of, well, there's Earth-sized target. Earth-like is different than Earth-sized, so they're gonna need to drill that down a little bit more. But yes, I do know where a lot of these targets are that they want to see. John Seville is commenting, if NASA keeps calling that telescope the Carl Sagan Space Telescope, it will be the first time a person has been honored twice. The Mars Pathfinder lander was named Carl Sagan Memorial Lander in '90s. That's right, it was. That's exactly right. But come on, it kind of deserves it, right? So let's see. I'm just scrolling back up. Okay, so I get this question a lot for some reason. Why didn't they make 2 JWSTs? It would have been cheaper in the long run, especially if it blows up on launch or doesn't unfold correctly. Why do you say that? Why do people say that, Stephen? I know you're thinking economy of scale. If we could just build 2 of these, it's cheaper than building 1 of these. But it's not. It's actually more. You have to spend money to build 2 very complicated telescopes. Even if the second one doesn't cost as much as the first, it's still more money that you have to spend, money that you don't have. So JWSTs cost around 10 billion to get this far. And then we've still got to operate the thing. And let's say we built another one using the same components. How much less would it cost? Not that much. And it's still 5, 6, 8 billion dollars more than you have. Then you've got to launch it. Then you've got to deploy it. Then you got to pay for. So all of this stuff, I don't get that. I understand that when you build more than one of something, you have backups, there is some economy there, but it's not in actual dollars. You don't build it for just a small fraction more. It's a lot fraction more. And JWST damn near got canceled with the money that it's costing now. So I never understood this about why don't we just build 2 in case one blows up? There's no money for that. And that's part of what was alluded to in this Decadal survey. We're doing this big observatory thing wrong. We need to mitigate these risks so that we're not blowing up this. Now, if we go to this new approach where they break down the science a little bit, they mature the technology, they build 1 JWST at some reduced capacity or with some technology that needs to mature before they actually launch it, then maybe you're right. Maybe then you could build another one to do more things, or at the same time, even with some technologies, and launch and have more of them that way. But we've got to get the cost down, and we've got to get the time it takes to launch these things down as well. It takes too long. 2 decades is way too long to wait. So we got to do a better way of doing this. And maybe your idea would work if they did this new approach. I don't know anything about costing projects, but it doesn't make sense to me that when you're struggling to build one, if I'm struggling to build one thing, whatever it is, at a huge amount of cost, why would I want to go along parallel with that and spend even more money on another one in case the first one doesn't work? I don't see the risk mitigation there. And thank you, VO. Thank you, man. You're out of this world. You're cool. Thank you for doing that. Thank you. This poor little channel needs all the help it can get. Ryan. Hi, Ryan. It's good to see you again. That really wide field telescope that was donated. Yes, that's the one. That's the one. So let's see. Yes, Chad, this is the channel that had the most important image ever taken. It was my first video I ever posted back in 2006. I want to thank Kevin, by the way. Kevin he called Special K on Discord. He reached out to me recently and gave me a story about how the Deep Astronomy channel helped him go into a career in astronomy. And I've invited him on a stream because I would love for people to hear his story. He said one of the things he liked about this channel was that I was one of the people who was talking about what it was like to have a job in astronomy. What it's like to get to work in the field. And that was information he really wanted to know, and it helped him. And now he's in a PhD program, and I think he's in Ireland right now. And so thank you, by the way. Thank you very much, Kevin, Special K, for that. I appreciate it. It makes me feel really good when I get that kind of feedback. So all the best luck of luck to you. Become an awesome astronomer. This is all about you guys. Your generation of astronomers are going to get to use JWST. You're going to get to enjoy the Nancy Grace Roman Space Telescope. You're going to be the first to get data from the Vera Rubin Observatory, the 30-meter telescope, the Giant Magellan Telescope. All of these are for you guys. And your generation is going to be able to see the universe in a way that my generation could only dream of. And while the Hubble was a magnificent leap for us in terms of capability and understanding of our place in the universe, it's going to pale in comparison to what JWST is going to show us, and these other observatories that are coming up are going to show us. I'm very excited about the future for you guys. And you guys will be looking back on this and go, remember when we thought dark matter was a thing? So anyway, I really think that you guys are amazing. So NASA built 2 Viking landers just in case the first one failed. Also, I think that's why there are 2 Voyager probes. No, there was 2 different. There were 2 different paths they wanted to follow. All were cheaper than a JWST though, but it doesn't cost 2 times. I know it's not double, but when you're talking $8, $9, $10 billion to have an extra $6 billion, say it costs 6 to build another one. Where's that money coming from? And why? Just to have it on standby? I think the way they built it, yeah, man, it's scary AF. All in on this launch, right? I get it. It's scary beyond belief. But I just don't see NASA ever having that capability to build 2 of these things and have one on standby. We don't give NASA that kind of money. Now, if this were, the military, that's a different question. Of course, they would need that capability to back up in case of a threat somewhere. We value that much more than we do scientific discovery. I'm not saying it shouldn't be done. I just think that in the environment and the amount of money we give NASA, it's just a pipe dream. There's no way you're going to get stuff like that. Let's see. Psyched for JWST. This is from Andy Tom. Thanks again for the video on Triangulum. Much neglected, yes, galactic neighbor. Still my fave channel, and I'll be watching you cover the imaging to come soon. Thank you, man. I appreciate that. That was part of Your Sky Tonight. I stopped doing that because I wasn't getting any feedback on it, and they didn't seem to be getting a lot of views until I recently went back and I looked at how many views How to Find the Andromeda Galaxy got. And I think, well, I guess there is some interest in this. So I don't know. I mean, like I said at the top of this hangout, it's a lot more fun for me to do these live streams because I get to talk to you directly than it is for me to upload a video, edit the video, shoot the video, and then upload it and wait for comments and stuff. And besides, the comments are usually, on YouTube, they can be pretty bad. So I don't really like to go to the comment section on YouTube very much. So this is why I do this kind of content. It's just more fun. Let's see. And Mladen is commenting, oh yes, if someone deserved that is the name of in the name of loved Carl Sagan, I think there's no doubt that we need one great important space telescope with Carl Sagan's name on it. It just makes sense, doesn't it? It just seems like we should have one already. We should have a Carl Sagan Space Telescope. We just, CSST. We need one of these. I definitely agree. I hope they end up calling it that. So Jimmy D, down from down under, will there be a live stream for the launch? I'm going to do yes, to answer your question. Today, I missed it because I was getting ready for this stream, but at 2:30 today, NASA did a science press conference on JWST I wanted to attend, but I was too busy getting ready for this. But yes, I'm going to restream whatever NASA streams, and I'll be there. So let's hang out together. Definitely. I don't care. I don't care what time of the day or night it is. I don't even know when the launch time will be, but I'm there. I'm definitely going to be there. Brandon's also commenting, would it be a good example of a good astronomy project where building many copies of something would be a good use of economies of scale to use? What would be a good example of that? I see. Well, the thing is, right, these are almost all one-offs by definition, right? We would like a telescope that can show us, that can directly image an exoplanet. That's what we want. And it just so happens that that telescope design is good for other things, right? You can use it for other stuff. But we tend to think like that. We tend to think of, I want a telescope that can show me this, right? And it's the same kind of question a lot of amateurs have to answer themselves when they go shopping for a telescope for themselves. It'd be like, well, what do I want to do with this telescope? Before I buy one, I need to think about what I want it to do with it, and buy the telescope that meets that, most of those criteria. And you're not going to find one that meets them all. So you kind of have to narrow it down. But what would be a good example? A space telescope where you had many of them. Well, one example is one we've already done, which was stereo. Stereo A and B look at the sun in two different two different locations to give us nice 3D views of activity on the sun. I was going to say something like Gaia, but I don't know if you had multiple Gaias up in space, if you can get parallaxes any easier than what you could with just one. But that's another example that pops into mind. The thing is, optical and infrared and UV telescopes you can't add them up in an interferometry kind of way as easily as you can with radio. But you could build an array of smaller, let's say, optical telescopes and connect them via interferometry, like they do with the VLT in Chile. The ESO has the VLT, which connects 4 telescopes via this way. That would be another example where if you launch, say, a bunch of, I don't know, 1 meter class space telescopes and then bunched them all together, you would get a much larger telescope out of it. That might be another way to do it. So there's one example I can think of. There's probably others, but I can't think of any right now. It's a good question, though. Hans is commenting, telescopes are like TVs. When you buy it, you think the size is right, but after a short while of using, you wish you bought the one that was larger. Yeah, I remember when I bought a 40-inch television, and I thought, oh, this is going to be great. I'm never going to need anything greater. Then I saw the 60s, and I'm like, oh, wow, that's really nice. So yeah, you're right. And aperture, and for me, I'm a visual astronomer. I like to look through an eyepiece. And so for me, I have to I talked about this on the last Space Junk podcast, where it's like I have a 20-inch reflector that I kind of need because I like to look through an eyepiece. And to look through an eyepiece, I need to overcome the light pollution and the poor seeing with aperture. And so I have a large light collecting area to overcome the poor seeing. However, if I were an imager, I wanted to take a lot of pictures, refractors these days are doing a pretty good job. 100, 120 millimeters is a great size for a lot of these cameras now. So yeah, you kind of have to think about what you want to use it with. In my case, bigger is definitely better because I like to use an eyepiece. Now, it's not so great for imaging because of its short focal length, and it's long focal length, and it's just unwieldy to move around. But it is a go-to telescope, so I can use it in that way. I just don't ever use it that way. Could we ever build a ground-based telescope to do this? Sure, except we're limited by what wavelengths you can see. The problem with the ground is always you can't do anything on the ground in ultraviolet or anything shorter the shorter wavelengths, because the atmosphere blocks it out, and the many areas of the infrared are also opaque to the atmosphere. So you can't. There's a lot. Optical, near infrared, and radio are the best bets for ground-based observatories, and that's why you always see them. But there's some things you can only use you can only get in space. So, all right, guys, I'm going to have to stop there. I will be back next Tuesday. I don't know what I'm going to talk about. Been so busy getting ready for this one. So I'll be back this next Tuesday and again on Thursday. Look for this channel. I'll post the events as in advance, so you can hit the little reminder button and things like that to see the next one. I have a whole list of ideas that I want to do. I could do at least a hangout. There's a hangout I want to do on terraforming the moon. But all of these take a lot of work for me to do. There's a question that somebody raised about can a massive star go straight into a black hole? I want to look into that. So I already did the space, the technology one. So there's lots I want to do. Detecting gravitational waves with pulsars. So lots of things I want to try, but I have to get prepared. I'm not sure what I'm going to do yet, but I will come back on Tuesday and we'll talk about whatever it is. If you have any ideas, get on the Discord server and tell me about them. And that's the best way to reach me. Thank you, Uncle Bill, for everything you've done. By the way, on Discord for the server. You have been a rock star in keeping this a great place and great resource for people. So please join it. Okay, I'll see you guys next week. I hope you guys have a great weekend. Thank you all so much for watching. And as always, keep looking up.